How does NTFS compression affect performance? I've heard that NTFS compression can reduce performance due to extra CPU usage, but I've read reports that it may actually increase performance because of reduced disk reads. How exactly does NTFS compression affect system performance? Notes. I'm running a laptop with a 5,400 revolutions per minute hard drive, and many of the things I do on it are I/O bound. The processor is AMD Phenom 2 with 4 cores running at 2.0 GHz. The system is defragmented regularly using UltraDefrag. The workload is mixed read-write, with reads occurring somewhat more often than writes. The files to be compressed include a selected subset of personal documents, not the full home folder, and programs, including several, less demanding, games and Visual Studio, which tends to be I/O bound more often than not.
I've heard that NTFS compression can reduce performance due to extra CPU usage, but I've read reports that it may actually increase performance because of reduced disk reads. Correct. Assuming your CPU, using some compression algorithm, can compress at CMB/S and decompress at DMB/S, and your hard drive has write speed W and read speed R. So long as C and GT, W, you get a performance gain when writing, and so long as D and GT, R, you get a performance gain when reading. This is a drastic assumption in the right case, since Lempel-Ziv's algorithm, as implemented in software, has a non-deterministic compression rate, although it can be constrained with a limited dictionary size. How exactly does NTFS compression affect system performance? Well, it's exactly by relying on the above inequalities. So long as your CPU can sustain a compression/decompression rate above your HDD write speed, you should experience a speed gain. However, this does have an effect on large files, which may experience heavy fragmentation, due to the algorithm, or not be compressed at all. This may be due to the fact that the Lempel-Ziv algorithm slows down as the compression moves on, since the dictionary continues to grow, requiring more comparisons as bits come in. Decompression is almost always the same rate, regardless of the file size, in the Lempel-Ziv algorithm, since the dictionary can just be addressed using a base plus offset scheme. Compression also impacts how files are laid out on the disk. By default, a single compression unit is 16 times the size of a cluster, so most 4 kilobits cluster NTFS file systems will require 64 kilobits chunks to store files, but does not increase past 64 kilobits. However, this can affect fragmentation and space requirements on disk. As final note, latency is another interesting value of discussion. While the actual time it takes to compress the data does introduce latency, when the CPU clock speed is in gigahertz, i.e. each clock cycle is less than 1 ns, the latency introduced is negligible compared to hard drive seek rates, which is on the order of milliseconds, or millions of clock cycles. To actually see if you'll experience a speed gain, there's a few things you can try. The first is to benchmark your system with a Lempel-Ziv-based compression/decompression algorithm. If you get good results, i.e. C and GT, W and D and GT, R, then you should try enabling compression on your disk. From there, you might want to do more benchmarks on actual hard drive performance. A truly important benchmark, in your case, would be to see how fast your games load, and see how fast your Visual Studio projects compile. Dr. Compression might be viable for a file system utilizing many small files requiring high throughput and low latency. Large files are, and should be, unaffected due to performance and latency concerns.
I explained it here in the Wikipedia entry for NTFS. NTFS can compress files using LZNT1 algorithm, a variant of the LZ7723. Files are compressed in 16 cluster chunks. With 4 kilobits clusters, files are compressed in 64 kilobits chunks. If the compression reduces 64 kilobits of data to 60 kilobits or less, NTFS treats the unneeded 4 kilobits pages like empty sparse file clusters. They are not written. This allows not unreasonable random access times. However, large compressible files become highly fragmented, as then every 64 kilobits chunk becomes a smaller fragment. 2425. Compression is not recommended by Microsoft for files exceeding 30 MB because of the performance hit. Citation needed. The best use of compression is for files that are repetitive, written seldom, usually accessed sequentially, and not themselves compressed. Log files are an ideal example. Compressing files that are less than 4 KB are already compressed, like zip or JPG or AVI, may make them bigger as well as slower. Citation needed. Users should avoid compressing executables like exe and DLL. They may be paged in and out in 4 kilobits pages. Compressing system files used at bootup like drivers, NTLDR, winload.exe, or bootmer may prevent the system from booting correctly. 26. Although read-write access to compressed files is often, but not always, 27, transparent, Microsoft recommends avoiding compression on server systems and or network shares holding roaming profiles because it puts a considerable load on the processor. 28. Single-user systems with limited hard disk space can benefit from NTFS compression for small files, from 4 kilobits to 64 kilobits or more, depending on compressibility. Files less than 900 bytes or so are stored with the directory entry in the MFT. 29. The slowest link in a computer is not the CPU but the speed of the hard drive, so NTFS compression allows the limited, slow storage space to be better used, in terms of both space and, often, speed. 30. This assumes that compressed file fragments are stored consecutively. I recommend compression only for files which compress to 64 kilobits or less, E1 piece. Otherwise, your file will consist of many 64K or less fractions. Midifrag does a better job of defragging.
You have a quite slow disk, so your question does have merit. NTFS compression is processor intensive and is tuned for speed rather than compression efficiency. I would expect that you would see a very small improvement for read operations. However, when accessing a file residing in the system cache, you will have a performance hit, since it will have to be decompressed again on every access. You will of course see that write operations will be slower because of the additional compression. Copying files on this same NTFS disk requires decompression and compression, so these will suffer the most. NTFS compression can also increase fragmentation significantly, but this is not a problem for most typical computers under typical workloads. Many types of files, such as JPEG images or video or zip files, are basically uncompressible, so these files will be slower to use and without any space saved. Files smaller than one disk cluster, typically 4K, are not compressed, as there is no gain. However, even smaller cluster size is sometimes advised when compressing the entire volume. NTFS compression is recommended for relatively static volumes or files. It is never recommended for system files or the user's folder. But as hardware configuration varies from one computer model to another, depending on disk, bus, RAM and CPU, only testing will tell what the exact effect of compression will be on your computer model.
It will make operations slower. Unfortunately, we cannot measure exactly how much or how little it will affect your system. When a file that is compressed gets open, it takes processor power to uncompress the file so the system can use it. When you are done with it and hit save, it uses more processor power to compress it again. Only you can measure the performance though.